Our galaxy is held together by a ghost. The Milky Way spins at over 500,000 miles per hour, a speed that should tear every star into the void. Yet it remains perfectly intact, bound by an invisible force we call dark matter. By the end of this journey, you will understand the immense, hidden architecture that dictates the fate of every galaxy. What keeps stars from flying off into nothingness, and what strange particle could form an entire cosmic skeleton we cannot see? How much of reality remains hidden from our eyes? This contradiction was first captured in precise, undeniable data by a scientist named Vera Rubin. In the 1970s, Rubin focused her telescope on the serene spiral arms of distant galaxies, meticulously charting the orbital speed of their stars. She expected a familiar pattern, one governed by the same gravity that rules our solar system. Out here, planets obey a simple law. Mercury, close to the Sun's immense gravity, races along its orbit. Neptune, far out in the cold dark, moves at a leisurely pace. Rubin anticipated galaxies would work the same way. Stars near the bright, crowded core should orbit quickly, pulled by the visible mass there. Stars out in the sparse galactic suburbs should slow to a crawl, but her measurements revealed something impossible. The stars at the very edge of the galaxy were not slowing down. They were whipping around just as fast as the stars near the center. The galaxy's rotation curve, as it's called, was flat. This was the galaxy rotation problem, and it shattered a fundamental assumption. The gravity from all the stars, gas, and dust we could see simply wasn't enough to hold those outer stars in place. They should have been flung into the intergalactic void. The only logical conclusion was that there had to be more, much more, than what our telescopes could capture. Vera Rubin's work provided the first solid evidence that galaxies are wrapped in enormous, invisible halos of something. This missing mass, whatever it was, exerted a gravitational grip strong enough to keep entire galaxies from spinning themselves apart. Her discovery shifted the entire field of astronomy. It was no longer enough to just study the lights in the sky. We now had to grapple with the profound shadow they cast. Rubin's work showed us the ghost's handiwork within our galactic home. But the true scale of its influence required looking far beyond the Milky Way, into the deep field where light itself becomes a messenger of the unseen. This brings us to the second, even more dramatic clue, one written in the very fabric of reality. It begins with a prediction from Albert Einstein. His theory of general relativity proposed that mass does not simply pull on objects, it warps the stage upon which everything plays out. Think of spacetime as a vast, taut rubber sheet. Place a heavy bowling ball in the center, and the sheet dips. Now roll a marble across that warped surface, and its path will curve, not because a force is pulling it sideways, but because it is following the new, bent geometry of the sheet itself. Light, Einstein realized, must behave the same way. A beam of light from a distant star, traveling past a massive object like our Sun, should follow this curved path, making the star appear in a slightly different position in the sky. This was confirmed during a solar eclipse in 1919, a triumph that reshaped physics. But astronomers soon realized this cosmic trick could be used for something even more profound. When the foreground object is not a single star but an entire cluster of galaxies, an immense knot of mass, the warping becomes extreme. The light from galaxies billions of light years behind this cluster does not just shift a little. It is bent, stretched, and smeared into strange arcs and multiple images, like looking at a distant street lamp through the bottom of a wine glass. This is gravitational lensing, and it acts as nature's ultimate scale. By measuring how severely the light is distorted, scientists can weigh the lensing cluster. Time and again, they found a staggering discrepancy. the visible galaxies in the cluster, for all their billions of stars, accounted for only a tiny fraction of the mass needed to create such dramatic bending. The majority of the gravity, the true anchor warping space-time into this cosmic magnifying glass, was coming from something completely invisible, permeating the entire cluster. These observations did more than just confirm dark matter's existence. They mapped its architecture. The lensing arcs revealed how this unseen substance forms vast, diffuse halos that engulf entire galaxy clusters, serving as the gravitational glue that holds these colossal cities of stars together. It showed us that dark matter is not just a galactic ghost, but the primary sculptor of the universe's largest structures, a hidden framework upon which the luminous universe is merely draped. This gravitational map reveals a structure far more subtle than a simple shell. The dark matter halo is not a rigid casing around the galaxy, but a vast dynamic sphere, a three-dimensional ocean of unseen particles. Its density is not uniform. Imagine it like a cosmic cloud, thickest and most concentrated at the very heart of the galaxy, then gradually thinning out as you move toward the distant, faint edges. This immense sphere extends staggeringly far beyond the glittering disk of stars we see in photographs, its gravitational influence reaching out to command the paths of everything bound to the Milky Way, from distant globular star clusters to small satellite galaxies like the Magellanic Clouds. It forms a deep, invisible well, and every star, every speck of cosmic dust orbits within its slopes. The particles thought to compose this halo are among the most elusive in physics. They do not emit, absorb, or reflect light. They do not interact with the electromagnetic force at all. Their primary conversation with the visible universe is through gravity, the persistent pull that sculpts galaxies. They may also interact via the weak nuclear force, the same force behind certain types of radioactivity. But this interaction would be so feeble and rare that detecting it requires extraordinary patience and technology. This profound darkness is why we cannot see it, why we cannot touch it, yet its gravitational signature is etched into the very motion of the cosmos. To understand how a galaxy like our own forms, evolves, and survives for billions of years, we must first understand this invisible architecture. It is the foundational blueprint, the hidden framework that dictated where the first stars could ignite and how the majestic spirals we admire could slowly take shape. Without this pervasive, dynamic halo, the universe would be a very different and far more lonely place. The identity of this ghostly particle remains one of physics' most compelling puzzles. We have mapped its gravitational shadow with incredible precision, yet we still do not know what it is. The search has narrowed to two primary suspects, each representing a radically different vision for the fundamental nature of reality. The first candidate is known as a WIMP, an acronym for Weakly Interacting Massive Particle. Imagine a particle that is heavy, perhaps dozens or even hundreds of times the mass of a proton, but one that communicates with our world only through gravity and the weak nuclear force. This makes it fantastically elusive. To catch one, scientists have built extraordinary traps. They construct detectors of ultra-pure materials, like liquid xenon or germanium crystals, and then bury them a mile or more underground, in old mines or beneath mountains. This subterranean fortress shields the experiment from the constant rain of cosmic rays and other background noise that could create false signals. The hope is that, very rarely, a WIMP from our galaxy's vast halo will drift through the chamber and bump into the nucleus of an atom in the detector. This collision would be incredibly subtle, a mere whisper of energy, but it would leave a telltale signature of light or charge. Teams across the globe, in laboratories from Italy to South Dakota to China, wait in profound silence for this faintest of cosmic knocks. The other leading candidate turns this idea of mass completely on its head. It is called the action. If a WIMP is thought of as a heavy subatomic boulder, and action would be more like a cosmic feather, astonishingly lightweight, perhaps a trillionth the mass of an electron. This particle emerges not from dark matter theory directly, but from a deep puzzle in quantum physics concerning the symmetry of forces. The action's proposed behavior is just as strange as its origin. In the presence of a tremendously strong magnetic field, theory suggests an action could spontaneously convert into a faint microwave photon, a particle of light we could actually detect. So while WIMP hunters listen for nuclear recoils in deep, dark quiet, action seekers are building powerful magnetic resonators, essentially high-tech radio receivers, and tuning them across countless frequencies, hoping to hear the distinctive tone of a dark matter particle singing into existence as a photon. This decades-long race is more than a technical competition. It is a profound quest to touch the hidden architecture of the universe. The discovery of either particle would not just solve a cosmic mystery, it would open an entirely new chapter in physics, revealing a fundamental component of reality that has been flowing through us and through everything we see for all of time. Yet the story of dark matter is written not just in what we see, but in what we fail to find. The most powerful supercomputers on Earth have spent decades simulating the birth and growth of galaxies within their vast dark matter halos. These virtual universes, governed by the laws of physics as we understand them, produce a very specific prediction for a galaxy like our own. Our Milky Way should be the center of a bustling galactic metropolis, orbited by a swarm of hundreds of small, dense satellite galaxies, each held within its own tiny clump of dark matter. When astronomers point their telescopes to our cosmic neighborhood, however, the sky tells a different story. We see only a few dozen of these satellite galaxies, not the hundreds the simulations demand. This is the long-standing missing satellites problem, a quiet but persistent gap between our theoretical blueprint and the observed universe, but the plot thickens further. The handful of small galaxies we do find circling the Milky Way, like the Large and Small Magellanic Clouds, seem oddly fragile. The computer simulations suggest that the most massive dark matter clumps around us should be strong enough, their gravity so potent, that they simply could not fail to form bright, star-filled galaxies. Yet these predicted behemoths appear to be missing in action. The satellites we observe are less massive, less dense, and dimmer than they should be. This is the too big to fail problem. It is as if we had a detailed forecast for a major storm, but when we looked outside, we found only a light drizzle. These twin puzzles are not mere oversights, they are crucial clues. They suggest that our understanding of dark matter itself might need refinement. Perhaps dark matter particles are not completely cold and slow-moving, as in the simplest models, but possess a faint warmth or wave-like property that smooths out the smallest clumps, preventing them from forming. Alternatively, the answer may lie in the complex, turbulent physics of star formation within these tiny halos. Maybe supernova explosions or radiation from the first stars blew away the gas needed to make new stars, leaving these small dark matter clumps permanently dark and invisible to our telescopes. Each possibility opens a new window into the hidden forces that shape galactic ecosystems. These are not failures of theory or observation, but the exciting friction points where our models meet the real, messy cosmos, compelling us to look deeper and think differently about the invisible architecture holding everything together. The true power of this invisible architecture is revealed only when we pull back to see the universe on its grandest possible scale. Forget single galaxies for a moment and consider the entire observable cosmos. What we find is a structure of breathtaking elegance and complexity, a vast network often called the cosmic web. This is dark matter's ultimate masterpiece, the skeleton upon which all visible light is hung. In the earliest moments after the Big Bang, the universe was a nearly smooth soup of energy and particles, but it was not perfectly uniform. Thanks to quantum fluctuations, tiny ripples existed in the density of dark matter, regions that were ever so slightly thicker than others. Over billions of years, gravity relentlessly amplified these small differences. The slightly denser patches pulled in more dark matter from their surroundings, growing heavier and pulling in even more. This process sculpted the primordial cosmos into an immense three-dimensional spiderweb, a labyrinth of dense filaments connecting at massive, crowded nodes, with enormous, empty voids stretching between them. This is the cosmic web, and its primary building material, its steel and concrete, is dark matter. Ordinary matter, the atoms that make up stars and planets and us, was merely a passenger in this gravitational construction project. After the universe cooled enough for atoms to form, this normal gas simply followed the gravitational blueprint laid down by the dark matter. It flowed along the invisible filaments, pooling in the deepest gravitational valleys at the intersections where it could collapse, ignite, and give birth to the first galaxies and the brilliant clusters we see today. Think of it like water flowing into a canyon system carved by an unseen force. The rivers of gas follow the pre-existing channels, and the cities of light, the galaxies, bloom where the channels meet. Our own Milky Way, with its vast dark matter halo, is not an isolated island. It resides within one strand of this universal tapestry. We are part of a filament, a thread in the grand cosmic weave, with other galaxies strung along this same invisible line, all of us moving according to the gravitational pull of a structure we cannot see. This realization reframes everything. Every brilliant galaxy cluster, every sweeping spiral, every quasar shining across billions of light years is just a decoration, a bit of luminous froth on the surface of a deep, dark ocean. The true structure, the foundation of all cosmic architecture, is this ghostly web of unseen matter, a scaffold built in the darkness that determined where the lights of the universe could ever turn on. This hidden blueprint does more than just hold the galaxy together. It writes its entire life story. The dark matter halo is not a static cage. It is a dynamic sculptor, an invisible hand that guides the galaxy's evolution from a faint whisper of gas to a brilliant spiral of light. It begins with the most fundamental act of cosmic creation, the birth of a star. For a star to form, vast clouds of hydrogen gas need to cool down, contract, and eventually collapse under their own gravity. But this process has a fierce opponent, the sheer kinetic energy of the gas itself, which wants to keep it hot and diffuse. The dark matter halo provides the essential counterweight. Its immense, pervasive gravity creates a deep, overarching potential well, a kind of cosmic basin that confines the gas, making it easier for local pockets to overcome their internal pressure and condense. The mass and size of the halo directly dictate the pace of this stellar nursery. A more massive halo in the early universe could pull in gas more quickly and from a wider region, potentially leading to a ferocious burst of star formation, a brilliant but short-lived fireworks display. A quieter, more gradually growing halo might foster a slower, steadier trickle of new stars across billions of years, like a long-burning ember. This is why, by studying the properties of a galaxy's halo today, astronomers can read backward through time. They can reconstruct its growth spurts, its periods of famine, and even its most violent chapters. The majestic spiral shape of our own Milky Way, with its distinct central bulge and sweeping arms, is not an accident. It is a direct consequence of how its dark matter halo formed and spun, gently shepherding the ordinary matter into that iconic pinwheel pattern we see today. The halo's gravity set the rules for the dance, and the stars and gas simply followed. But the story grows more dramatic when galaxies meet. When we look out into the universe, we see galaxies colliding in slow motion, their stars swirling together in great tidal streams of light. What we are witnessing, in truth, is not primarily the collision of stars. Space is too vast for that to happen often. we are seeing the merger of their dark matter halos. These immense, invisible structures are the true protagonists of the encounter. They interact first, their gravitational forces intertwining and tangling, dictating the entire choreography of the merger. The visible galaxies are just luminous tracers, like flecks of foam on the surface of two merging whirlpools, showing us where the deep, dark currents are flowing. Our own Milky Way bears the scars of such ancient mergers. The faint streams of stars orbiting in the galactic halo, the oddball stars moving in the wrong direction. These are the archaeological remnants of smaller galaxies that were long ago torn apart and absorbed by our dominant dark matter halo. Each of these events added more mass, more stars, and more history to our galaxy, each one a chapter written by the invisible hand. By mapping the halo's present-day structure and motion, scientists are not just studying a container, they are reading a biography. They can trace the lineage of our galaxy, identify its long-lost siblings, and even predict its ultimate fate in a future collision with the great Andromeda galaxy. It is a profound realization that the history and destiny of every glittering city of stars is authored not by the light we see, but by the pervasive, unseen darkness that cradles it from beginning to end. To truly understand this hidden architect, we must build universes from scratch. This is the realm of cosmological simulation, where the world's most powerful supercomputers are tasked with a single, monumental job: to rewind time to the first moments after the Big Bang, fill a virtual cosmos with dark matter, and then press play. Scientists begin by programming these machines with the fundamental laws of physics, as we know them: gravity, the expansion of space, the behavior of particles. They then seed this digital void with the same tiny density ripples we believe existed in the infant universe. From this simple, elegant starting point, they unleash the most powerful force in cosmology, the relentless, patient pull of gravity, and let the simulation run for billions of virtual years in a matter of weeks. The results are not just data, they are visions. Projects with names like IllustrisTNG and EAGLE generate breathtakingly realistic virtual universes, vast digital cubes of space spanning hundreds of millions of light years across. Within them, you can watch the cosmic web emerge from nothing, see dark matter condense into intricate filaments and halos, and witness ordinary gas flow along those invisible channels, cooling and collapsing to ignite the first virtual stars and galaxies. These are not artistic renderings, they are rigorous mathematical predictions. The galaxies that form in these simulations have realistic sizes, shapes, and distributions. They spin at the right speeds, they cluster together in ways that mirror our deepest sky surveys. When the simulation is complete, researchers can fly through this synthetic cosmos, comparing its structure pixel by pixel to the maps we have made of the real night sky. This process turns the supercomputer into the ultimate laboratory. Since we cannot manipulate dark matter in a jar or observe a single galaxy's entire life, we can run countless experiments in silico. What happens if dark matter particles are slightly warmer and faster moving? How does a galaxy's spiral structure change if its halo formed from several smaller mergers instead of one large collapse? Does adding the furious energy from supernova and black holes to the simulation help explain why some small dark matter clumps remain dark, solving the missing satellites problem? Each simulation is a test, a way to see if our theories, when played out to their logical conclusion over cosmic time, produce a universe that looks like home. When they do not match, as with the initial predictions for satellite galaxies, it is not a failure. It is a crucial clue, a signpost pointing toward a missing piece of physics, perhaps a new property of dark matter itself, or a more complex understanding of how stars form. These virtual universes are our proving grounds, allowing us to stress test reality itself. to run the tape of cosmic history over and over until the story told by the light finally aligns with the story written by the invisible. But what if the ghost isn't there at all? For all the evidence pointing to an invisible substance, a small but persistent group of physicists asks a far more radical question. Could we be misinterpreting the clues entirely? Perhaps the problem is not with the universe, but with our understanding of one of its most fundamental forces. This idea challenges the very need for dark matter by proposing that our theory of gravity itself is incomplete on the vast, diffuse scales of galaxies. It is called modified Newtonian dynamics, or MOND. The central premise is startlingly simple. What if gravity does not fade with distance in the exact way Isaac Newton and Albert Einstein predicted? In the intense gravitational fields of our solar system, their equations work flawlessly, predicting the orbits of planets to breathtaking precision. But in the outer realms of a galaxy, where a star feels only the faintest tug from the collective mass far away, MOND suggests gravity behaves differently. It proposes a new, very subtle rule that gives gravity a tiny extra kick when it becomes extraordinarily weak. This single adjustment can mathematically reproduce the flat rotation curves of galaxies, the very phenomenon that first hinted at dark matter. Without invoking a single unseen particle, MOND can explain why those distant stars whip around so quickly. They are not held by an invisible halo. They are simply responding to a slightly stronger pull from the visible galaxy than our standard laws predict. It is an elegant solution, paring away the need for a mysterious, undetected substance. Yet elegance alone cannot conquer the cosmos. As astronomers have gathered more evidence from across the universe, MOND has faced profound challenges. It beautifully explains the rotation of individual spiral galaxies, but it struggles to account for the bullet cluster, a system where two galaxy clusters have violently collided. Observations show that the mass causing the most severe gravitational lensing, mapped by the bending of light, is clearly separated from the visible galaxies. This is exactly what you would expect if dark matter, which does not interact with itself or normal matter in messy collisions, had sailed through the crash, leaving the visible gas behind. For MOND to explain this, it would require a major, untested revision to explain how gravity can be divorced from visible mass in such a dramatic way. Furthermore, the detailed structure of the cosmic microwave background, the ancient afterglow of the Big Bang, shows a pattern of tiny temperature variations that act as a blueprint for the early universe. The standard model of cosmology, with dark matter as a central ingredient, predicts this pattern with remarkable accuracy. Reproducing that same cosmic fingerprint with a modified gravity theory, while also matching the growth of the cosmic web, has proven incredibly difficult. This is not a battle of right versus wrong, but a vital tension at the frontier of science. The debate between an unseen particle and a revised force pushes the boundaries of fundamental physics, forcing us to question our most basic assumptions. It reminds us that every cosmic mystery is also a mirror, reflecting the limits of our current understanding and compelling us to look deeper, to question more thoroughly, and to remain open to the possibility that the truth may be stranger than any single idea we have yet conceived. Our galaxy's dark halo leaves fingerprints in the light. To chart this invisible territory, astronomers have turned to a remarkable celestial phenomenon, stellar streams. Picture a long, shimmering river of stars flowing in a graceful arc across the blackness of the galactic halo. This is not a structure born whole, but a ghost, the final breath of a smaller system that ventured too close. These streams are the shredded remains of ancient globular star clusters or tiny dwarf galaxies, captured and then slowly torn apart over billions of years by the Milky Way's immense gravitational tides. As these streams of stars continue their long orbits, they do not travel through empty space. They move through the unseen ocean of dark matter that makes up our galaxy's halo, and its invisible currents leave a mark. If the dark matter halo were perfectly smooth and spherical, these stellar rivers would trace simple, predictable paths. But the halo is lumpy and dynamic, its density fluctuating with clumps of dark matter and the gravitational scars of past mergers. As a stellar stream passes through these unseen irregularities, its delicate ribbon of stars gets tugged and distorted. The stream might warp, kink, or even gap, its stars scattered from their pristine line. This is where our most powerful telescopes become instruments of cosmic cartography. Missions like the European Space Agency's Gaia spacecraft are performing a monumental census, precisely measuring the position, motion, and distance of over 1 billion stars. By focusing on these faint stellar streams, scientists can use them as the most sensitive probes imaginable. By tracking exactly how a stream is being bent and pulled, they can work backward to map the distribution of the mass that is doing the pulling. It is a process akin to mapping the contours of an invisible mountain range by watching how wind currents flow over it, or deducing the shape of a submerged landscape by tracing the path of a river on the surface. Each distortion in a stellar stream is a data point, a clue to the hidden geography of the dark matter halo. Some streams suggest the halo is slightly flattened, like a squashed sphere. Others hint at vast, diffuse clumps of dark matter orbiting unseen within it. With every new stream discovered and mapped, we add another line to the blueprint, slowly revealing the true shape and texture of the ghost holding our home together. The silence in these laboratories is not empty, it is charged with anticipation. To hunt a ghost, you must first retreat from the world. A mile beneath the Black Hills of South Dakota, in the darkness of a former gold mine, scientists have built a trap of exquisite sensitivity. It is called LUX-ZEPLIN, and it is designed to listen for the faintest whisper of a collision in the night. At its heart is a chamber containing 10 tons of liquid xenon, purified to an almost unimaginable degree. This is the target. The idea is both simple and profound. At any given moment, countless particles from our galaxy's dark matter halo are thought to be streaming through Earth and through us. Almost all of them pass through unnoticed, but very, very rarely one might interact. If a WIMP, a weakly interacting massive particle, were to bump into the nucleus of a xenon atom in that deep tank, the impact would produce 2 signals, a tiny flash of light and a small pulse of electrical charge. The entire apparatus is built to amplify and record these infinitesimal signatures, but to hear that cosmic whisper, you must eliminate every other sound. That is why the detector is buried under a mountain of rock, which acts as a shield against the constant rain of cosmic rays from space. It is housed within a tank of ultra-pure water to block natural radioactivity from the surrounding stone. The xenon itself is chilled to -100 degrees Celsius. Every component is selected for its incredible purity. This is science conducted in a cathedral of quiet, where researchers wait for a single, decisive event that has not yet come. A similar vigil is held under the Gran Sasso mountain in Italy, where the XENONnT experiment also watches over a multi-ton xenon target with relentless precision. These are not passive observatories, they are active traps set in the deepest quiet humanity can create. They operate at the very edge of detectability, pushing engineering and patience to their limits. The fact that no definitive signal has been found is in itself a powerful result. It has ruled out vast swaths of possible properties for dark matter particles, narrowing the search and forcing physicists to consider even more exotic possibilities. This relentless, quiet work in the deep places of the world is a testament to a profound commitment to touch the intangible and finally bring the universe's most abundant yet elusive architect into the light. While underground laboratories listen for quiet collisions, other eyes are turned upward, scanning the heavens for a different kind of signal. If we cannot see dark matter directly, perhaps we can witness its final moments. Some compelling theories suggest these ghostly particles are not completely immortal. In certain models, when two dark matter particles meet, they could annihilate one another, transforming their mass into a burst of pure energy. In others, a single unstable particle might slowly decay. Both processes would produce a shower of standard particles we know how to detect, especially high-energy gamma rays, the most powerful form of light in the universe. This turns the quest into a cosmic forensics investigation. We may never find the body, but we might find the smoking gun. To conduct this search, scientists use instruments like the Fermi Large Area Telescope, a powerful observatory orbiting Earth. It does not look for visible starlight, it scans the entire sky for gamma rays, building a map of the universe's most violent and energetic phenomena. The strategy is to look for places where the gamma ray signal is stronger than it should be. The dense center of our own Milky Way, where dark matter is thought to be most concentrated, is a prime target. If annihilation or decay is happening anywhere, it should be brightest there. Astronomers also look at the diffuse glow of our galactic halo, and even at small, faint dwarf galaxies that are believed to be almost pure dark matter, with very few stars to create confusing background signals. The hunt has produced tantalizing hints. There is a curious, unexplained excess of gamma rays emanating from the galactic center, a glow that does not perfectly match known sources like pulsars or gas clouds. It fits roughly what some dark matter models predict, yet the case remains frustratingly open. The signal could still be explained by a population of unknown, conventional astrophysical objects. Distinguishing between an exotic dark matter signature and a new class of pulsar is incredibly difficult with current data. Every potential signal exists in a haze of cosmic background noise. This makes indirect detection a high-stakes treasure hunt, where every anomaly is scrutinized, debated, and held to the most rigorous standards. A confirmed detection would not just reveal dark matter, it would tell us something profound about its nature, that it can interact with itself in ways beyond gravity. For now, the high-energy sky whispers with possibilities, its brightest mysteries still holding their secrets close. At the very heart of our galaxy, where the stellar traffic is thickest, sits a silent giant. Sagittarius, a star, is a supermassive black hole, weighing in at over 4 million times the mass of our Sun. Its immense gravity dominates the chaotic core, but it does not act alone. It exists within and is fundamentally shaped by the galaxy's vast dark matter halo. This creates a profound cosmic partnership between the most invisible objects and the most pervasive substance. One leading theory proposes that the black hole's incredible gravity acts as a cosmic fishing net for dark matter particles. As these ghostly particles orbit through the halo, those that pass too close to Sagittarius, a star, could have their paths bent, causing them to swing back around again and again. Over eons, this could lead to an extraordinary buildup, a dense, invisible spike of dark matter crowding the space immediately around the black hole. In such an extreme environment, the possibility for interaction skyrockets. If dark matter particles can annihilate each other, this spike would be the furnace where it happens most intensely. The energy released from countless annihilations could, in some models, actually feed back into the black hole itself, providing a slow, steady trickle of mass that influences its growth over billions of years. It might also produce a unique flash of gamma rays or other particles, a beacon we could potentially detect from Earth, a signal from the shadowy heart of our galaxy. But the relationship flows both ways. The dark matter halo is not just a backdrop, it is the architect of the traffic flowing into the core. The halo's overarching gravitational well sets the routes for everything moving within the galaxy. Clouds of gas, doomed stars, and even smaller stellar mass black holes all follow the invisible contours laid down by the dark matter. Their long, slow spiral inward is choreographed by the halo's gravity, a gradual infall that ultimately delivers fuel and companions to the waiting supermassive black hole. This intricate dance solves a persistent mystery. Supermassive black holes in many galaxies, including our own, are surprisingly quiet, not consuming matter at the furious rate their size might suggest. The dark matter halo may be the reason, acting as a cosmic regulator. By controlling the pace and the pathways of material falling toward the center, it prevents the black hole from feasting too quickly, maintaining a stable galactic ecosystem. This frontier of galactic dynamics reveals a universe of hidden connections, where the invisible hand of dark matter guides the fate of the most enigmatic objects in existence. The future of our galaxy is written in invisible ink. We have traced the history of the Milky Way through the scars of ancient mergers, but its ultimate fate is already set, a slow-motion collision on a scale that defies human imagination. In roughly 4.5 billion years, the Milky Way will meet its closest cosmic neighbor, the great Andromeda Galaxy. Right now, Andromeda is a faint, fuzzy patch in our night sky, but it is on a direct course toward us, closing the distance at 250,000 miles per hour. When this event unfolds, it will not be the cataclysmic explosion of stars we might picture. Space is too vast and stars are too small. Instead, it will be a profound and gradual gravitational dance, and the lead dancers will be the things we cannot see. The first act of this cosmic merger will be performed entirely by the dark matter halos. Long before the outer stars of the two galaxies even begin to mingle, these immense, invisible spheres will start to interact. Their gravitational fields will reach out, intertwine, and pull on one another. Because dark matter does not interact with itself through any force but gravity, the halos will do something extraordinary. They will pass right through each other. Think of two vast clouds of smoke slowly drifting into the same space, their edges blending and merging without a single spark or collision. This first passage will set the entire tempo for what follows. As the halos swing past each other and then fall back together, their combined gravity will rewrite the rulebook for every star, every planet, and every speck of dust in both galaxies. The familiar spiral arms of the Milky Way will be stretched and torn into long, streaming tails of stars. The beautiful pinwheel structure we know will dissolve into chaos. Over billions of years, as the dark matter halos finally settle into a single, new, and larger halo, the stars will settle with them. They will be flung onto new, randomized orbits, no longer confined to a thin, spinning disk. The result will not be a grander spiral, but a vast, featureless blob of stars, a giant elliptical galaxy that astronomers have already named Andromeda. This future galaxy's shape, size, and very existence are being dictated right now by the properties of the halos we cannot see. Their total mass determines how violent the merger will be. Their distribution guides how the stars will be scattered. The dark matter is the silent director of a billion-year ballet, the choreographer ensuring that from this immense collision, a new, stable galactic home will eventually emerge. It is a humbling perspective to realize that the fate of our entire solar neighborhood, the future night sky of whatever beings might look up from Earth's distant descendants, is being orchestrated not by the brilliant stars overhead, but by the profound and pervasive darkness between them. The sharpest test of our theories often comes from the smallest galaxies. In the faint, wispy glow of dwarf galaxies orbiting our own, astronomers have found a puzzle etched into the very center of their invisible halos. Our most sophisticated computer simulations give a clear prediction for the shape of a dark matter halo. Gravity, acting over billions of years, should sculpt it into a very specific profile. The density should rise steeply and sharply toward the very center, forming what is known as a cusp. Imagine a mountain with a narrow, pointed peak. The heart of the halo should be the most dense, crowded region of all. Yet when scientists study the motions of stars within real dwarf galaxies, the data tells a different story. Instead of a steep cusp, many of these galaxies appear to have a core, a central region where the dark matter density is nearly flat, like a plateau or a gently rounded hill. This is the cusp versus core problem, and it strikes at a fundamental question: is dark matter truly as simple and non-interactive as our simplest models assume? One compelling explanation suggests that dark matter might have a hidden social life. In the simplest cold dark matter model, these ghostly particles pass through each other without a second thought, like starships in the vast emptiness of space. But what if, very rarely, they can actually interact with each other through some force besides gravity? If dark matter particles can scatter off one another, this would act like a subtle form of friction in the densest central regions. Over cosmic time, this self-interaction could smooth out the sharp peak, transferring energy from the inner particles to the outer ones, effectively eroding the cusp into a soft, constant density core. It is a tiny modification to the theory, but one with profound implications, suggesting dark matter has a richer internal physics than we ever imagined. The other leading possibility places the blame not on dark matter, but on the furious energy of star formation. In the early lives of these dwarf galaxies, the first generations of massive stars would have lived fast, died young, and exploded as supernovae. These titanic detonations would have blasted waves of energy and gas outward from the center. This cyclic fury could have physically pushed against the gravitational pull of the dark matter, sloshing it around and gradually sweeping it from the center, carving out a core in what was once a cusp. This scenario paints a more dynamic picture of galactic evolution, where the visible universe does not just passively follow the dark matter blueprint, but can actively reshape its invisible foundation through bursts of brilliant, violent light. Solving this mystery is not just about fixing a plot hole in a simulation. It is about understanding the rules that govern the halo's architecture on the smallest scales. Does dark matter have a hidden complexity, a whisper of interaction that only reveals itself in these dense, ancient hearts? Or is it the ordinary matter, in its most explosive moments, that holds the power to sculpt the dark? The answer will tell us not only what dark matter is, but how it dances with the light across the full span of cosmic time. This unseen architecture holds a profound philosophical weight. For all of human history, our understanding of the cosmos was built upon what we could see, touch, and measure directly. The night sky was a tapestry of lights, and those lights were the universe. Dark matter shatters that assumption completely. We now must accept that over 85% of the matter in the cosmos is made of something we cannot perceive with any of our senses. It emits no light, reflects no signal, and passes through our finest instruments without a trace. The universe we experience, with its brilliant stars and swirling galaxies, is just the visible frosting on a cake whose substance we cannot taste. This is a humbling recalibration of our place in reality. Our intuition, so finely tuned for the world of solid objects and direct cause and effect, is ill-equipped for a cosmos where the dominant component is forever hidden. We are forced to rely on a different kind of sight, one built from mathematics, from the subtle bending of light, from the precise orbital dances of distant stars. We must trust the indirect evidence, the shadow cast by the unseen. This is the true power of the scientific method, not just to explain what we can observe, but to confidently infer the existence of realities that lie permanently beyond our direct perception. It reshapes our cosmic self-image. We are not merely inhabitants of a material world, but observers in a universe where the majority of the script is written in invisible ink, a constant reminder that reality is far richer, stranger, and more mysterious than our everyday experience could ever suggest. The search for dark matter's identity may require us to rewrite the rules of reality itself. For over a century, physics has been split into two magnificent, yet stubbornly separate kingdoms. On one side, we have the quantum world governing the bizarre behavior of subatomic particles, a realm of probabilities, entanglement, and discrete packets of energy. On the other, we have Einstein's general relativity, which masterfully describes the grand cosmic dance of gravity as the curvature of spacetime itself. These two theories are titanic successes in their own domains, but they speak entirely different languages. Where they should meet, at the heart of a black hole or in the first instant of the Big Bang, our understanding breaks down into paradox. To solve the deepest mysteries of the cosmos, including perhaps the origin of dark matter, we need a unified framework, a single set of laws. This is the quest for a theory of quantum gravity, and it may hold the key to our ghostly halo. In this pursuit, ideas like string theory or loop quantum gravity offer radically new visions of reality's foundation. String theory, for instance, proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating strings. The different vibrational modes of these strings could give rise to all the particles and forces we know, from electrons to photons. Crucially, this framework might naturally include new, stable vibrational patterns that do not interact with light, particles that would be perfect candidates for dark matter. They would not be an awkward add-on to our physics, but an inevitable consequence of the universe's underlying geometry. Similarly, other approaches suggest dark matter could be a topological defect, a kind of cosmic knot or texture frozen into the fabric of spacetime during the universe's rapid expansion and cooling in its first fleeting moments. Think of it like the cracks that form in ice as water freezes, a permanent imprint of a dramatic phase transition. If this is true, then the dark matter halo cradling our galaxy is more than just an invisible structure, it is a living fossil. Its distribution, its clumpiness, the very way it flows, could be a direct record of the universe's birth pangs, carrying information about physics at energies so high they make the Large Hadron Collider seem like a child's toy. By mapping the halo's subtle architecture today, we are not just doing astronomy, we are performing an archaeological dig into the first fractions of a second after everything began. The properties of this unseen matter could be our only window into an era when all the forces of nature were one, a time before time as we know it existed. In this light, dark matter transforms from a missing puzzle piece into a cosmic messenger, a relic from the dawn of everything, waiting silently in the dark to tell us how the story truly started. This hidden architecture may have written the conditions for life itself. While dark matter does not interact with the chemistry of biology directly, its gravitational presence sets the cosmic stage upon which the drama of life can unfold. Its most profound contribution is one of stability. The Milky Way's majestic spiral disk, where our solar system resides, is a relatively calm and orderly place, especially in our galactic suburb. This long-term peace is not an accident. The immense spherical dark matter halo acts as a gravitational anchor, dampening violent oscillations and preventing the disk from becoming wildly unstable or warping severely over time. This stability is a prerequisite for life as we understand it. It allows planetary systems like our own to form and persist for billions of years within predictable orbits, free from the constant gravitational upheaval that would scatter protoplanetary dust or fling nascent worlds into the cold void. In a more chaotic galaxy without this invisible anchor, the quiet, multi-billion-year processes of planetary formation and biological evolution might never get a chance to begin. Our solar system's location is also a gift of this architecture. We orbit far from the chaotic, radiation-flooded galactic core, in a region where the dark matter halo's steadying influence helps maintain a tranquil environment. This galactic habitable zone, a concept extending the idea of a star's habitable zone, is thought to be a narrow band where conditions are just right, not too close to the dangerous center, not too far out in the star-poor hinterlands. The gravitational framework of the halo is instrumental in carving out and preserving such quiet neighborhoods, beyond mere stability, more speculative ideas push the boundaries of possibility. Some researchers have pondered whether dark matter could play a more direct, if subtle, role. If certain types of dark matter particles can be captured by a planet's gravity, they might occasionally interact with ordinary matter in its core. These incredibly rare events could deposit tiny amounts of energy, contributing a faint internal heat source. For a large rocky planet, this effect would be negligible compared to radioactive decay, but in certain exotic models, it could theoretically help maintain geological activity over astronomical timescales. Another fascinating, though highly speculative, line of thought connects dark matter to life's catalysts. The halo is not perfectly smooth. It contains streams and clumps. As our solar system orbits the galaxy, it periodically passes through these denser patches. The subtle gravitational nudges from these invisible clouds could, in theory, disturb the distant reservoir of icy bodies in the Oort cloud, sending a shower of comets inward toward the Sun. While such comet showers are often discussed in the context of mass extinctions, they are also a potential delivery mechanism for water and organic compounds to inner planets, the very ingredients necessary for life to spark and evolve. These ideas remain on the fringe of science, vivid hypotheses awaiting evidence. Yet they serve a powerful purpose. They expand our perspective. They invite us to see dark matter not just as a cosmic scaffold, but as a silent participant in the grand narrative. The invisible halo that keeps the stars in their courses may have also, indirectly, cleared a peaceful stage and perhaps even delivered some of the raw materials, setting in motion the slow, beautiful process that led, on at least one small world, to creatures who could look up and wonder about the darkness holding them safe. Across the cosmic web, a new kind of messenger is delivering clues. These are fast radio bursts, or FRB, some of the most enigmatic signals in the universe. For just a few milliseconds, a source in a galaxy billions of light-years away releases a colossal flash of radio waves, a burst of energy equivalent to what our Sun puts out over several days. Then it vanishes. Their origins are still debated, involving magnetars, merging neutron stars, or other extreme cosmic events. But for cosmologists, the true value of an FRB is not necessarily where it comes from, but the incredible journey it takes to reach us. Each burst is a pristine probe, fired on a billion light-year trip through the deepest reaches of intergalactic space. As this flash of radio waves travels, it does not move through a perfect vacuum. It traverses the diffuse sea of electrons that fills the space between galaxies, a thin plasma that is part of the cosmic web's ordinary matter, and this encounter leaves a fingerprint. The radio waves, which are all emitted at the same instant, do not arrive at our telescopes at the same time. The lower frequency waves interact more with these free electrons, slowing down just a fraction more than the higher frequency waves. The result is that the burst gets stretched out or dispersed across the radio band. By measuring this dispersion, how smeared out the signal becomes, astronomers can calculate the total number of electrons the burst encountered along its entire path. This is where the connection to dark matter becomes profound. The distribution of these free electrons is not random. It follows the gravitational blueprint of the cosmic web. Where the dark matter filaments are densest, they pull in more ordinary gas which contains those electrons. Therefore, by using an FRB to count the electrons along a specific, precise line of sight, scientists are indirectly weighing the total mass, both visible and dark, that shaped that corridor of space. Think of it like measuring the humidity in the air to infer the shape of an invisible mountain range influencing the weather patterns. A single FRB gives us one clean measurement along a single needle-thin beam through the cosmos. But as we detect more of these bursts from different directions and different distances, we can begin to triangulate. We can compare the dispersion from an FRB that passed through what we believe is an empty void versus one that sliced through a known filament of the cosmic web. The differences in those measurements tell us about the density of matter in those vastly different environments. This technique offers a powerful, independent check on our maps of the dark matter halo. It could reveal whether the halo's outer regions are as diffuse as we think, or if there are hidden substructures clumping within it. Because FRBs come from such immense distances, they allow us to probe the dark matter distribution on scales and along sight lines that other methods cannot easily reach. Each brief, brilliant flash is like a lightning bolt in a cosmic storm, illuminating for a fleeting instant the entire hidden landscape between galaxies, giving us a new way to weigh the ghost that holds it all together. This monumental search has no single headquarters or national flag. The hunt for our galaxy's invisible architect is a story written by thousands of hands across the globe, a testament to what humanity can achieve when we turn our shared curiosity toward the heavens. It is one of the most profoundly international endeavors in the history of science. In the silent darkness a mile beneath South Dakota, the LUX-ZEPLIN detector waits. Across the ocean, under the limestone of the Italian Apennines, the XENONnT experiment maintains its own vigil. These are not competitors in a race, but complementary ears listening for the same cosmic whisper, their data pooled, their methods scrutinized, their null results as valuable as any signal. This collaboration extends far beyond underground caverns. In space, the Fermi Gamma Ray Space Telescope, an international mission, scans the high-energy sky, its data streams analyzed by teams from universities in Japan, France, the United States, and beyond. On the ground, an intricate network of optical and radio telescopes, from the high deserts of Chile to the peaks of Hawaii, collectively maps the gravitational lensing and stellar streams that trace the dark matter halo's shape. Every major discovery or puzzling anomaly is immediately shared across continents, picked apart in virtual conferences that span time zones, and tested against independent observations. This is how modern cosmology works, not in isolated ivory towers, but in a vibrant, global conversation. The quest demands this scale of cooperation because the mystery itself is so vast. No single nation, no single experiment could possibly corner the market on understanding a substance that makes up most of the universe's matter. The technological challenges alone are staggering, requiring advances in ultra-pure materials, quantum sensors, cryogenics, and data processing that push the very limits of human engineering. By sharing the burden and the brilliance, we accelerate the path to knowledge. This collective effort does more than just combine resources. It builds a robust and self-correcting process. A claimed signal in one lab must be verified by another. A new map of the halo from one telescope array is cross-checked against simulations run on supercomputers in a different country. This constant, respectful challenge is the engine of scientific progress, ensuring that when we finally do touch the dark, the evidence will be undeniable. In this light, the search for the galaxy's hidden halo becomes more than a physics problem. It is a unifying human project, a rare frontier where our common desire to understand the cosmos transcends borders and backgrounds. We are all, literally, living within the mystery we seek to solve. The particles streaming through an Italian lab are the same ones flowing through a South Dakota mine and through each of us. This shared predicament, this universal immersion in the dark, inspires a shared mission. It is a powerful reminder that some questions are so fundamental, so woven into the fabric of reality, that answering them requires the combined focus, ingenuity, and hope of our entire species, looking up together into the same star-filled, yet mostly dark sky. Another possibility for our galaxy's ghost is not a particle at all, but a forgotten population of ancient relics. Could the dark matter halo be made of black holes, not ones born from dying stars, but from the chaotic birth of the universe itself? This is the speculative idea of primordial black holes. The concept takes us back to the universe's first fleeting moments, a time of unimaginable density and turbulence. According to this theory, during that extreme infancy, random fluctuations in density could have been so intense that pockets of space simply collapsed under their own weight, instantly and spontaneously forming black holes. These would not be the stellar mass black holes we know from supernova, nor the supermassive giants at galactic centers. Primordial black holes could have any mass, from smaller than an asteroid to larger than a star, forged in the furnace of creation before the first atoms even existed. For dark matter, the most compelling candidates would be on the smaller end, perhaps with masses comparable to a large mountain or a small planet. Trillions upon trillions of these microscopic, asteroid mass black holes could be swarming through the galaxy's halo, each one a tiny, invisible knot of pure gravity. Their collective mass would perfectly explain the gravitational pull we measure, and their nearly undetectable nature would account for their invisibility. They would simply be there, ancient fossils drifting through the dark, their combined presence holding the stars in place. The beauty of this idea is its stark simplicity. It requires no new, exotic particles, just gravity acting on structures born from the universe's own violent beginnings. Yet to be viable, these primordial black holes must have left some trace, and that is where the theory faces its greatest tests. Scientists have devised clever ways to hunt for them. One method relies on a phenomenon called gravitational microlensing. If a primordial black hole from our halo passed directly between Earth and a distant star, its gravity would act as a tiny lens, bending the starlight and causing the star to temporarily brighten in a very specific way. Astronomers have conducted massive, long-term surveys monitoring millions of stars, searching for these telltale flashes. So far, the number of observed events is far too low to account for all dark matter, severely limiting how much of the halo could be made of black holes in certain mass ranges. Another crucial constraint comes from the ripples in spacetime itself. When two black holes spiral together and merge, they send gravitational waves echoing across the cosmos. Observatories like LIGO and Virgo have now heard many of these cosmic collisions. The rate and masses of the black holes they detect tell a story. If the universe were teeming with enough asteroid mass primordial black holes to explain dark matter, they would frequently pair up, get caught in each other's gravity, and merge. The predicted rate of these small mergers would create a background hum of gravitational waves that we should be able to detect. Current observations have not found that signal, placing another strong limit on the idea. While these constraints make it unlikely that primordial black holes constitute 100% of dark matter, they have not ruled them out entirely. A small fraction of the halo could still be composed of these ancient objects, or they might exist in a narrow mass window that has so far escaped our searches. The enduring appeal of this speculation is what it represents, a reminder that the universe's first second was a place of such incredible energy that almost anything could have been forged there. The true nature of the invisible halo might not be a sea of unknown particles, but a cloud of cosmic artifacts, leftover scars from the moment of creation itself, forever orbiting in the dark. The profound mystery of the halo has sparked a parallel journey, one not of detection but of expression. While physicists hunt for particles, a different community of creators asks a compelling question: how do you give form to the formless? Artists, musicians, and designers are translating the cold data of cosmological simulations into works that engage our senses, building a vital bridge between the abstract equations of science and the human need to perceive. This is more than just illustration, it is an act of shared discovery. Take data sonification, where scientists transform the parameters of a dark matter simulation into sound. The density of the halo might become a deep, resonant drone, while the motion of particles within it rises as a shimmering, ethereal chorus. Listening to such a piece, you do not just hear numbers, you feel the scale and the flow of this invisible ocean. It becomes a ghostly symphony composed by the universe itself and interpreted through human creativity. Sculptors, too, grapple with this invisible architecture. Some use intricate webs of wire or glass to model the cosmic filamentary structure, creating tangible objects you can walk around, whose shadows cast a visible web upon the wall. These works make a crucial point: the dark matter halo is not an empty shell, but a dynamic, three-dimensional scaffold. By walking through a physical representation, even an artistic one, the mind grasps the concept of a pervasive structure in a way a graph on a screen cannot convey. Perhaps most powerfully, immersive digital installations allow participants to step inside a visualization of the halo. Wearing a virtual reality headset, you can float amidst a galaxy of light, and then with a toggle, watch as the brilliant stars fade to reveal the immense, glowing lattice of dark matter that holds them all in place. This shift in perspective is transformative. It viscerally communicates the central revelation of modern cosmology, that the universe we see is a decoration on a hidden framework. These artistic endeavors serve a profound purpose beyond beauty. They are tools of communication, making the scale and significance of dark matter tangible for a public that may never read a scientific paper. They democratize understanding, inviting everyone to contemplate the hidden architecture of reality. In doing so, they remind us that science at its best is a deeply human endeavor, driven not just by the pursuit of facts, but by a fundamental urge to expand our collective imagination, to envision and connect with the profound truths that lie just beyond the edge of sight. The invisible architecture of our galaxy has escaped the lab to fuel our grandest stories. Long before Vera Rubin charted her flat rotation curves, the human imagination was already drawn to the idea of hidden worlds and unseen forces. Today, dark matter has become a staple of science fiction and popular culture, a blank canvas upon which we project our deepest hopes and fears about the cosmos. In the universe of Star Trek, it is often a navigational hazard or a mysterious energy source, a plot device that embodies the unknown dangers lurking between the stars. In Philip Pullman's celebrated trilogy, His Dark Materials, it is reimagined as dust, a conscious elementary particle that represents wisdom, sin, and the very essence of human experience. These are not scientific descriptions, of course, but they are powerful cultural translations. They take an abstract, intimidating concept from astrophysics and give it narrative weight, turning a cosmological ingredient into a character, a moral force, or a source of ultimate power. This process of storytelling is profoundly human. Faced with a mystery as vast as dark matter, we instinctively try to fit it into a story we can understand, to give the invisible ghost a face and a role in our cosmic drama. These fictional portrayals, for all their creative liberty, perform a vital service. They act as a gateway. A viewer intrigued by a Star Trek episode featuring a dark matter nebula, or a reader captivated by Pullman's metaphysical dust, might feel that first spark of curiosity. That spark can lead them to search for articles, watch documentaries, and ultimately discover the real, and in many ways more astonishing, science behind the fiction. In this way, culture becomes a collaborator in discovery, lowering the barrier to a complex idea and inviting a wider audience to ponder the same profound questions that keep cosmologists awake at night. The prevalence of dark matter in our stories also serves as a cultural barometer. It shows that this scientific concept has successfully permeated our collective consciousness. It is no longer confined to academic papers and conference halls. It is part of the shared language of wonder. When a video game uses a dark matter drive as the ultimate engine, or a film depicts a weapon that harnesses its power, it reflects a society grappling with a new cosmic reality, one where most of the universe is made of something we cannot see. This cultural digestion of science enriches both domains. It gives artists and writers a rich, new vocabulary of ideas to explore, themes of hidden reality, unseen connections, and the limits of perception. For scientists, it is a reminder that their work resonates far beyond equations, touching the core of how we see our place in the universe. The fact that we weave dark matter into our myths and entertainment proves that the mystery matters, not just to telescopes and particle detectors, but to the human spirit that seeks to find meaning and story in the dark. The hunt for our galaxy's ghost is about to receive a monumental upgrade. A new generation of cosmic observatories, now under construction or awaiting launch, is poised to transform our understanding of the invisible halo from a collection of clues into a detailed, three-dimensional map. These are not merely better telescopes, they are entirely new kinds of eyes, each designed to see a different signature of the unseen. On a mountain top in Chile, the Vera Rubin Observatory is preparing for a mission of staggering scope. Its enormous mirror and giant digital camera will, over 10 years, scan the entire southern sky every few nights. This relentless survey will do more than just take pretty pictures. It will create a cosmic movie, capturing the subtle motions and changes of billions of celestial objects. For dark matter hunters, this data will be a goldmine. The observatory is expected to discover and map tens of thousands of new stellar streams, those faint rivers of stars torn from ancient galaxies. By tracking how each stream is warped and kinked by the halo's invisible lumps, Rubin will provide the most comprehensive chart yet of the dark matter distribution in our galactic neighborhood, revealing its true shape and texture in unprecedented detail. Meanwhile, in the quiet of space, the Nancy Grace Roman Space Telescope will take a wider view. With a field of view 100 times larger than the Hubble Space Telescope, Roman is designed to conduct vast, deep surveys of the cosmos. Its primary mission includes studying dark energy, but to do that, it must also meticulously map dark matter. It will achieve this by observing weak gravitational lensing on a colossal scale. By measuring the subtle, coherent distortions in the shapes of millions of distant galaxies, Roman will trace the distribution of all mass, visible and invisible, across enormous swaths of the universe. This will allow scientists to see how the cosmic web of dark matter has evolved over billions of years, testing our theories of how this invisible skeleton grew and how it guides the formation of galaxies. Then there is the sound of the dark. The Laser Interferometer Space Antenna, or LISA, is a revolutionary mission that will listen not for light, but for the ripples in space-time itself. Consisting of 3 spacecraft flying in a precise triangular formation millions of miles apart, LISA will detect low-frequency gravitational waves, the kind produced by the slow, spiraling dance of supermassive black holes at the hearts of merging galaxies. This is where dark matter's influence may sing. As these monstrous black holes orbit each other, their motion is governed by the dense spike of dark matter theorized to surround them. The gravitational wave signal LISA hears will encode the details of that dance, allowing physicists to weigh the black holes and measure the properties of the dark matter environment that shapes their final moments. It is a direct probe of the ghost's grip in the most extreme gravitational arenas in the universe. Together, these instruments represent a holistic assault on the mystery. Rubin will chart the local halo's anatomy through shredded stars. Roman will map its grand universal architecture through bent light. LISA will feel its influence in the echoes of colliding giants. The coming decade promises to replace our blurry sketch of the dark matter halo with a high-definition portrait, one that may contain features we have not yet even dreamed of, pushing us closer than ever to finally understanding the invisible architect of our galactic home. There is a quiet, humbling possibility we must now consider. What if the ghost remains a ghost forever? What if, despite our deepest minds and finest senses, the dark matter particle never gives us a direct, undeniable signal? Its nature could be so elusive, its conversation with ordinary matter so faint, that it slips through every net we cast, leaving only the gravitational shadow we have already mapped. This is not a failure of science, but a challenge to our expectations of how the universe must reveal itself. The evidence for dark matter's gravitational reality is now etched into too many independent lines of observation, from the rotation of galaxies to the bending of cosmic light. That evidence does not vanish if the particle hides. Instead, our relationship to the mystery would fundamentally shift. We would move from hunters of a specific particle to cartographers of a well-characterized yet invisible component of reality. Science could continue to map the halo's distribution, measure its influence on galactic evolution, and predict its role in the cosmic web with ever greater precision, all while acknowledging that its fundamental identity remains just beyond our physical grasp. This would be a profound but deeply acceptable outcome. It would stand as a powerful reminder that the cosmos operates by its own rules, not by our desire for tidy answers. The universe is under no obligation to make all its components accessible to our current technology or even to our current understanding of physics. A dark matter that interacts only through gravity would be a permanent testament to the limits of our perception, a dominant thread in the tapestry of reality that we can only feel by the way it pulls on everything else. This does not halt discovery, it redirects it. The quest becomes about understanding the architecture itself in perfect detail, about reading the history of the universe written in the distortions of this invisible medium, and about accepting that some of the greatest truths may be forever inferred, not directly seen. In a strange way, this possibility enriches the mystery, reminding us that wonder is not extinguished by uncertainty, but is often born from it. Our galaxy, and every glittering island in the cosmic sea, is held in the silent embrace of a ghost. This journey through the invisible shell of dark matter reveals a universe far stranger and more magnificent than it ever appears in a simple photograph. The brilliant stars we see are not the main story. They are luminous ornaments on a hidden framework, a vast and dynamic halo that cradles our entire Milky Way. This mysterious substance is the unseen architect, the gravitational sculptor that dictates the graceful spin of galaxies, guides their dramatic collisions, and weaves the immense cosmic web that spans the observable universe. From Vera Rubin's pioneering charts that first revealed the missing mass, to the profound quiet of laboratories buried deep beneath mountains, the quest to understand this darkness is one of the defining adventures of human curiosity. It is a story that stretches from the first instant of the Big Bang to the ultimate fate of our galactic home. While profound mysteries remain, from the identity of the particle to the subtle clues in dwarf galaxies, each new piece of the puzzle brings us closer to comprehending our true place within this hidden framework. We are not just inhabitants of a material world. We are observers in a cosmos where most of the script is written in invisible ink. Let this exploration be a reminder to always look beyond the visible, to question the empty spaces, and to embrace the wonder of inference. For the greatest stories, the most fundamental truths about our existence, are often written in the dark. If this journey into the invisible captivated you, consider subscribing for more deep dives into the universe's deepest secrets, and share your own thoughts on this cosmic mystery in the comments below.